theorem 5 up here on the board. This is the theorem that's going to formally state for us that the reciprocal of power functions goes to 0 as x goes to infinity or to negative infinity. It actually states it a little bit more because power functions have an integer, a positive integer in the exponent position. Here they're saying if r is any rational number, remember that's just any number that can be written as a ratio or a fraction of integers. Okay. Then the limit as we go off to infinity of 1 over x to the r is 0. Okay. So, for example, the limit as x goes to infinity of 1 over the square root of x. Well, I know that I can rewrite a square root as a fractional exponent. That's x to the 1/2. Applying theorem 5, this is going to be 0. Honestly, the way I would do this, though, I wouldn't bother to rewrite it. I'd just look at that and I'd say, oh, that's going off to infinity. But that's in the denominator. If the denominator goes to plus or minus infinity and the numerator doesn't, I've got something finite that I'm trying to divide up into lots and lots and lots and lots of pieces. The whole fraction is going to go to 0. Okay. I did want to just point out, because I think it's a good idea to read your textbook, and as you read the textbook, you might say, why did they say it has to be a rational number? Well, it actually doesn't. If we're going off to positive infinity, this would apply for irrational numbers too. So if I had the limit as x goes to infinity of 1 over x to the pi is an irrational number, that would also be 0. That is true. The book simply isn't including that as part of the theorem, and honestly, we're not going to encounter that much this semester. Okay. However, I think the reason they're restricting it to rational numbers is because we do run into an issue when we're taking a look. Oh, I'm sorry, this should have been negative infinity. We do run into an issue if x is going off to negative infinity, because not all powers are defined for negative numbers. For example, the 1/2 power we just said is the square root. We can't take the square root of a negative number if we're working in the real number system. Now, we could switch to working in the complex numbers, but then you're in an upper division class. If we're doing calculus this semester, we are just working in the real numbers. We can't take fractional powers of negative numbers if the fraction has an even denominator, because that would mean we'd be taking an even root of a negative number. So, they say if r is a rational number so that x to the r is defined for all values of x. The ones we're concerned about here are the negative ones. So basically that would mean r would have to be a fraction so that the denominator, when we write it in lowest terms, is odd, so that we're dealing with odd powers. If that's the case, so that this thing is defined, then we can take the limit as x goes to negative infinity of 1 over x to the r, and that would be 0. And because the reciprocal of x to a rational number is only defined for certain rational numbers, if x is negative, in this case, when we're going to negative infinity, we really can't work with irrational powers. Okay, so this is just the formal statement of essentially the chocolate cake principle. If you're dividing by, and the chocolate cake principle actually extends even further than this, because the chocolate cake principle would also say, for example, the limit as x goes to infinity of 1 over e to the x. That's going off to infinity. So, oops. So the fraction is therefore going to 0. Okay. So the theorem 5 is just a specific case of when you divide by something big, you get something small.